Okay.
Okay.
So yeah, so I'd like to just say a little bit about something connected to motives. So I'm going to give it this talk that I sort of practiced on you, and
when is that?
It's on Wednesday. Yeah, I'm about
Wednesday
to go.
this week.
Yeah, there's a Grothendieck conference this week near Riverside at Chapman University, and I'm gonna give a talk there about that. Just because I figured.
Sorry, are you showing something on the screen?
Not yet. I'm attempting to, or I am actually, but it's not what I want to be showing with you. I am.
Okay, but it's not my fault if I'm seeing something strange on the screen. Okay.
Yeah.
I can't hear you now. Okay, now I think I can hear you. Well, can I say words?
I'm gradually getting to what I actually want.
Okay.
This is not it.
Okay.
I'm going to stop showing my video because I seem to be overspeeding my poor little system here. So I was doing this example. Oh wow, I hit it exactly. So I was talking about this example here of
yes
points on this curve, and David Roberts is a guy in Australia, started asking me probing questions about this that was actually pretty fun. So because they forced me to think about a lot of stuff. So well, actually the true elliptic curve has one extra point. And so the true the true formula for the number of points of an elliptic curve due to Hasse is this thing where you have p to the n points over to the field with p to the n elements, and then one point, which you can think of as this point at infinity if you like, and then the exciting part are these terms that are complex conjugates of each other, so that they add up to something real and they grow like the square root of p to the n. So all the fun, in a sense, comes from that middle stuff. And so in terms of motives, what's going on is that your elliptic curve is breaking up into motives as direct sum of motives. And there's this 1 point motive, and then there's this Lefschetz motive, and then there's this interesting motive here, which has well, they use the word weight instead of dimension for motives. So this has a weight that's halfway between being the point has weight 0. These guys have weight 1. The curve, the Lefschetz motive has weight 2. So this is like a half dimensional kind of phenomenon. But anyway, so the interesting thing is that motive there corresponding to this for elliptic curves over finite fields, I believe I've read that motive there always is either an irreducible motive already. So like that's it. You've just broken up the motive into 3 parts, or it can split up into 2 summands itself. And so that made me, so David started pressing me on that issue.
When does that happen?
So there are tons. So I believe that happens when the elliptic curve is called supersingular, which is an old-fashioned.
I've heard it. I don't really know what it means.
That has nothing at all to do with singular varieties. It's sort of a misleading term, but what Hasse, well, so like for elliptic curves over the complex numbers, there are these sort of 2 different big cases. Either it doesn't have complex multiplication or it does have complex multiplication. And that sort of means, that's all about the endomorphisms of your elliptic curve. And whether it's just multiplication by integers or more to it. And so then it turns out that for elliptic curves over finite fields, you can get those two types of cases, but you can also get a third case, which is the supersingular case, where the endomorphism ring of the elliptic curve is, in some sense, even bigger, although it's finite. But what I mean by that is that the endomorphism ring can either just be generated by, it can either just be the integers, or it can be the integers generated by the integers and one extra endomorphism, or by two extra endomorphisms, in which case those endomorphisms form what folks call a quaternion algebra, which is a generalization of the quaternions that like includes 2x2 matrices. It's a central simple algebra. And so this particular curve that in my example, I just happened to, I was like trying to, so David asked me, okay, is that one supersingular or not? Is it breaking up into two parts or one? And that like really put me on the spot because I had no idea. But then Wikipedia has a pretty good article on supersingular curves, and it actually lists this particular curve as a supersingular curve over the field with two elements.
Sorry, where is the curve again? Can I see it?
Yeah, sorry. The specific curve that is my example curve is this one here. Well, this is like the affine equation for it.
Okay, and we're doing exactly that.
Yeah, well, that's the one I'm looking at.
Okay.
And it's super singular. And
okay, now go back to the other thing. Yeah.
Yeah. So, well, just an intermediate thing. So in this particular case, the thing I was calling alpha is -1 plus or minus I. And so then that's the alpha in this formula. So it turns out that there are not that many in the case of the field with two elements, there are not that many choices for what this alpha can be, because this number here has to be an integer. And even just the fact that it's an integer when n equals 1, that over the field with p elements that this works out to be an integer, puts really big restrictions on what alpha can be. And it turns out that the alpha can together with the fact that alpha has to have length equal to the square root of 2. So alpha has to have length equal to the square root of 2, so it lies on that circle. And then when n equals 1, this junk here is basically, without the minus signs, it's like twice the real part of alpha. So the real part of alpha has to be a half integer, or some half of an integer. So if you look for half integers that can be the real parts of a point on the circle of radius square root of 2, there are very few choices, and it's just -1, -1/2, 0, 1/2, and 1. It's like 1.5 is already bigger than the square root of 2, so that's too big. So I realized that like you can actually like dig into this a certain amount and see that like elliptic curves over the field with two elements, they have these like at most 5 choices for what this alpha can be. And then on the Wikipedia, it says that your elliptic curve over a field with two elements will always be supersingular if the curve has an odd number of elements. There's deeper reason for that.
Okay.
But this particular curve has 5 points. Did I say elements? I probably should say points. If your curve has 5 points, then you know right away that it's supersingular. And you can read off how many points it has just from looking at this formula here. And so you can see that in some of those cases that I enumerated just a second ago, you get that this number works out to be odd when n is equal to 1. And so those curves have got to be supersingular. And I don't know if the other ones are always not supersingular or not. But anyway, so it turns out that you can get into this sort of fine-grained structure of elliptic curves which I'm sort of curious about now. Part of why I'm curious is because I just wanted to know, like, what are all the motives that you can get that have this dimension, or this, they call it this weight. So this kind of junk is coming from a weight 1 motive. And I just have a feeling that it's possible to like completely understand the weight 1 motives. And so like, I'm pretty close to knowing something about them that come from elliptic curves. I don't know if all weight 1 motives come from elliptic curves, but I sort of think I read some stuff that makes it sound like that's true.
Weight 1?
Weight 1 means like these like these colored circles here, metaphorically speaking. So to the extent to which this term in the count of points has to do with these first homology of the torus, well, that's the motivation for that stuff being called weight 1. So I would call it dimension 1, but maybe dimension is confusing because there's this complex and real dimension. So weight is like real dimension. So weight goes 0, 1, 2 for these different terms in this thing. That's just the way they call it. So motives have a weight that's a natural number.
Sorry, but is it like, what should I be thinking of it? Should I be thinking of it as being like the index of the cohomology group or something?
Yeah. Yeah. So there's so what
about other abelian varieties besides elliptic curves? Do they break up into motives having to do with elliptic curves or something? I mean, does my question make any sense?
It makes sense. So far, all I know is this. So by the way, a whole bunch of stuff about motives is reliant on Grothendieck's standard conjectures. So like there's a whole bunch of stuff that's not even known that should be known. So like one of the standard conjectures amounts to the fact that you can take any motive and it's a direct sum of motives of the different weights. So it's not even known. And now, to be technical, I'm talking about pure Chow motives, which are sort of the simplest ones in some way. Okay. Well, simple in some way. Simple in the sense of like being closest to what his Grothendieck's dream for motives was. So anyway, if you assume that kind, so maybe I'll assume that conjecture, all those conjectures, and then I read somewhere that over finite fields, motives. So you also get to pick coefficients when you're dealing with motives, which is different than the field that you're working over. So it's like coefficients in a cohomology theory. So I read somewhere that if you work with coefficients that are the complex numbers, then motives for finite fields are all built up out of motives coming from abelian varieties and motives coming from, they're called Galois motives, which are like representations of the Galois group of the finite field. So those latter kind are like 0-dimensional motives, I think. So like if you're like working over some finite field, then like any extension of that finite field is some kind of variety-ish thing over the finite field. So you know, it's some kind of space. It describes some kind of 1 point kind of space. It's like a fat point. I don't know technically what I'm saying right now, but anyway.
This is all very interesting and suggestive, but boy, do I have a lot to learn about this. Go ahead. Yeah. Go ahead.
Yeah. I mean, I definitely have a ton to learn about it. I mean, so anyway, that thing I read, which is like in somebody's talk about motives, some parent experts, it like refers to some paper that I haven't looked at. So it says that like if you're working with complex coefficients over finite fields to understand motives, can that actually be true? It seems too good to be true. I think the complex coefficients probably like wash out a lot of the fancy stuff, as you'd expect from cohomology theories. And so then they're saying like it's just representations of the Galois group and abelian varieties. So I don't know. Anyway, so that's what I know. I don't know your question. Like, can you get all this stuff from the higher abelian varieties out of the elliptic curves? I just don't know. But anyway, I'm going to keep. That's all I wanted to say. I'm just going to like keep chewing away on this a little bit, trying to learn what people know about it, because it seems like it's sort of fun and sort of concrete in some ways.
Well, let me ask a couple of questions, a couple of sort of follow-up questions to things you were telling me last time.
Sure.
And also things you're sort of telling me this time. Or things we were talking about last time. So we have, and also in email, we've been discussing various vague ideas about analogies between the Lefschetz, the Lefschetz motive is the one that gets inverted?
Yeah.
And the inverse is called the Tate motive, is that true?
Yeah.
And so we were kind of discussing analogies and or relationships between that and the idea of, in the world of stable homotopy theory, the one sphere and the negative one sphere as being inverses to each other with respect to smash product of spectrums. And so we're exploring very speculative analogies. But so one thing that I'm confused about is, so in the world of stable homotopy, obviously, the spectrums form an infinity, one category more than they form an infinity category. And the inverse relationship between the one sphere and the negative one sphere is presumably very affected by the fact that it's an infinity, one category. And but on the other hand, when I hear people trying to talk about motives and invent motives and say what motives are, sometimes they say that that at least the original idea was that they form a category, not like an infinity, one category, partially because maybe they weren't talking about infinity, one categories back then too much. But then you also made it sound like Voevodsky or somebody was exploring the idea of making motives or something like that into an infinity, one category or something like that.
Yeah, and I just want to say that, he seemed to make tons of progress that had been stuck before by doing that. So I mean, it's possible that that's what they should have been doing all along.
But there are some very special cases where you can actually get away with just ignoring the homotopy aspect and just thinking of it as actual categories or something like that. Is that right? I mean,
yeah. I mean,
some very degenerate case that you were talking about.
Well, yeah. I mean, so Grothendieck was just treating them as a category, and people sort of trying to follow up on his thoughts were doing that way. And it seemed like it could be really cool to do that, but it was like stuck by these standard conjectures. No one knew how to prove them. No one knew how to disprove them either. So so it's not clear if the stuckness is like lack of ingenuity, or whether this is like maybe. So now I'm beginning to now that we've been talking about this, I've been thinking like, oh, so maybe they should have been using an infinity one category. But I don't know. I don't know.
So my vague question and or comment was just along the lines of, if we try to explore analogies between the inverse relationship between alleged inverse relationship between Lefschetz and Tate motive analogies between that and the inverse relationship between the one sphere and the negative one sphere. To what extent is the attempt to construct such analogies, to what extent is that affected by the whole issue of whether we're dealing with categories versus infinity, one categories? So I don't really have anything intelligent to say about that, but I just wanted to raise that question.
Yeah. I think,
yeah,
one of the things Peter May did was to try to cook up a world where spectra were dealt with much more strictly than before. So it's possible.
It depends what you mean by strictly. I guess I know some of that, but go ahead. Yes.
Yeah. Okay. Well, maybe that's all I want to say. They were,
sometimes people make model categories out of spectrums or something like that, and
he was trying to make a world where,
yeah,
you could think of. Yeah, I don't know how related this is. He was trying to make a world where you could, maybe it's like a.
Well, go ahead.
He was trying to make a world where you could think of ring spectra as actual ring objects in some category of spectra. Whereas before people, and he succeeded, and whereas before people were like needing all this coherence law stuff. Well,
that's very interesting. That's very interesting. I'll have to learn.
But that's sort of more.
Yeah,
he'd love to talk about that. But so I don't know. So I mean, maybe it's one of these things where like you can do things more strictly at the expense of more ingenuity.
Sure. Again, I'm trying to invent the homotopy belief method. The belief method is already invented, but I think the homotopy belief method can also be invented. And if you actually get these machines up and running, then you can actually try to use them to ask and answer kind of some of the kinds of questions that we're dealing with here.
Do you have any?
Yeah.
You do sort of, but I'll ask you anyway. Do you have any nice examples where you use the belief method to throw in a formal inverse to something?
Sure. I mean,
like examples that are easier than motives and spectra.
Yes, I mean, I'm not sure how much more to get into this thing. This is a whole great topic all by itself. But I mean, I think we've already talked about the idea of a subline object. So right but we have the idea of an object that has a tensor inverse, in a 2 rig. But we also have the idea of an object whose am I saying this right? Whose exterior power is 0, whose exterior square is 0.
And it should probably be even. Wait, no. Anyway, those are most interesting to me when the object is even. But anyway, yeah, we've talked about this sub-dimension business before.
Yeah, so once you have an object like that, then you can formally invert it.
Huh.
And something interesting happens when you formally invert it. But
does it get to have dimension 1 then?
What actually tends to happen is the whole theory tends to break up into 2 pieces, one of which where the object has dimension 0 and the other one where it has dimension 1. Except don't trust me on that. I could be misremembering some of the details, but it's something like that. At least in some cases, it's something like that. And it's very interesting. It's very interesting to prove it. It's very interesting to work this out. But what was I trying to say? I mean, one of the things that's interesting about this is that when you construct the believers in the tensor inverse, the believers look very analogous to the spectrums of stable homotopy theory. I mean, in some versions of stable homotopy theory, the spectrums just look like objects that can be infinitely de-looped. So you have this whole sequence where you de-loop it, and then you de-loop it again, and you de-loop, and the whole sequence of those de-looping sort of is the spectrum.
Yep.
And you have something very much like that in the belief method. Whenever you're inverting an object that is already pre-invertible, and pre-invertible means something like being a subline object or something like that.
And de-looping involves, or looping involves the thing of maps, the internal thing of maps from the subline object to your object, your believer.
Yeah, so it's de-homing with respect to the thing that you're trying to invert. So de-looping is just, de-homing with respect to the circle. But you can do this more generally, de-homing from anything. Well, what I said from anything, but what I actually mean is
it goes bad.
What?
Does it go bad in some cases?
It's very interesting what happens. So you can do it with anything, but in some cases it sort of chokes and it gives a result, but there's a lot of collapsing that happens. But if so, it's sort of like this. It's sort of like, sometimes I joke about the idea that there's the different levels of the hierarchy, the cult hierarchy that you climb as you first you just believe in the properties, then you believe in the properties and structures, then you believe in the properties and structures and stuff. And in this picture, the inverse is kind of like stuff. But if you just start believing that an object has the property and the structure and the stuff to be an inverse, so that it actually has an inverse, then a lot of collapsing can happen. But if you do it step by step, then it's much more gentle. And so you'll see that all of the collapsing of certain kinds takes place in the initial steps. If you get to the step where you already have all the property and structure of being invertible, then the last step is just the de-looping, the infinite de-looping thing. So there's a very general result here about. I'm being very sloppy here. I'm not remembering all the details, but it's something like this. The general idea of inverting objects with respect to a tensor product can be very systematized, and the invention of spectrums presumably forms a special case of that, except that there's the whole issue of it being homotopy belief rather than the lower dimensional belief. Yeah.
What's it like to believe in the property of being invertible? How do you phrase that?
Again, it's a little bit ambiguous. It's sort of different kinds of property, but I think the kind of property we're talking about here. One way formally to say it is just you invert all the maps that become invertible by having a tensor inverse. So it's just a matter of inverting maps. You don't introduce any new morphisms or anything like that. So the believers don't have any operations on them. The believers are just objects that believe that certain maps are invertible. Whatever.
Yeah. Okay. That sounds like a property.
That's in this, and again, it depends on which belief doctrine. But in the belief doctrine that we're usually working with, the two-rig belief doctrine, it's like that. Believing in the properties. That means that all the morphisms get inverted that need to get inverted.
I'll have to think about that because I don't know what those maps are, but that may be fine for now.
Yeah, I'm not sure I have a good picture, concrete picture for the, I mean, if we're talking about the specific case of, I mean, what am I trying to say? I mean, it's probably true that for an invertible object, the action of all the permutation groups on all the tensor powers probably just reduces to actions of Z mod 2, that, you know, everything that's in everything that's in the alternating group acts trivia.
Huh.
So I think you would have to believe that every element of the alternating group on the tensor, you know, the nth alternating group on the nth tensor power, you have to believe that I'm guessing here, but you'd have to believe that that is acting trivially. And if you want to express that in terms of inverting a map, you could say that the co-equalizer between those elements and the identity element
Is invertible. The co-equalization map, or whatever you call it.
Yeah, something like that. Yes, I think that's right. I think you said it right. So I'm being incredibly sloppy.
Yeah. Well, okay.
Incredibly approximate answers, but right. I mean, right. If you pick a random object off the street, it doesn't have that property. It doesn't have the property that the alternating.
Right.
But these subline objects, I think they do have that property.
Yeah.
I think we would have to check that.
Line. Okay. Line objects do. I see. I think.
So at the if you're not working in the homotopy context, then the infinite delooping trick should work if you have an object that has that property. I think that already that object has the property that the alternating groups are acting trivially on it.
Mm-hmm. Okay, well, I resist the temptation to keep asking more about this stuff because it sounded like you had some other stuff you wanted to talk about.
Yeah. Yes. Still very disorganized, but yeah, I'm going to try something different now. Well, except that it's secretly exactly the same as what we've been talking about. Okay, so I'm going to try sharing screen here. Let's see. That was some days ago. Let me just, I'm still trying to perfect my note-taking stuff here. Okay, so Baez, add page, okay, new page. Okay, Monday, May 23rd, around 5 p.m. Okay. Actually, let me fix something. I'm doing this right? Okay. So, sorry, I'm just making a mess of my friend's apartment here. Let me just try to clean up little things here. Okay. Now, what am I trying to say? So, All right, let me tell you my vague plan for today. My vague plan for today is we're going to start thinking about the 20th. I just, 20 as an example. 20th cyclotomic field. And my plan, the reason I want to start thinking about the 20th cyclotomic field is I want to try to use it as a source from which to mine examples of abelian varieties. So we're going to try to extract all of the abelian varieties that we can think of from out of this source material. And this has a lot to do with what you were saying a moment ago about, well, when you were trying to explain supersingular to me, but it was like an extra twist to some story that involved elliptic curves, or more generally abelian varieties that do have complex multiplication or that don't have complex multiplication, or maybe that have something in between. Probably as you go up in the dimension of the abelian varieties, you probably get more different possibilities as to how much complex multiplication or what kind of complex multiplication there is.
Yeah, that would be fun. Yeah. So I was like, you can get like complex multiplication, or I like calling it quaternionic multiplication for elliptic curves. And that keeps on going. So are you going to focus on complex multiplication here? That is like one.
I think so. It could be that I'm accidentally going to fall into some quaternionic multiplication, but this idea of quaternionic multiplication.
That only happens.
Well, don't make me.
That might happen for abelian varieties of higher dimension, but yeah. But for
don't make me think about it yet.
Okay,
that sounds too interesting.
Okay.
So yeah, I don't really know what I'm doing, but I'm just gonna fake it here. We'll see how it goes. So first of all, I'm gonna try to think about what the Galois group of this field is, and use that to help us understand all the subfields of this field. And this is an example I've thought about a lot before. Which partially means that you may have heard me talk about a lot of these examples before. But it's fun to play around with, but it's also useful for certain purposes. Our purposes for today include trying to understand abelian varieties. We'll see how it goes. All right, so what is the 20th cyclotomic field? I guess we can sort of think of it as the rational numbers adjoin our favorite primitive 20th root of unity.
Mm-hmm.
And then, the Galois group is right. All the other, so this is kind of, am I saying this? Is this right? You can say that this, in a certain sense, this is the walking primitive 20th root of unity. So the automorphism group should consist of all the other primitive 20th roots of unity in this field. Mm-hmm. And, basically that would include things like 1 to the power of n over 20, where n is relatively prime to 20. That's pretty much what you need for it to be primitive. And so there's basically those 8 primitive elements, those 8 relatively prime things. It's basically GL1 Z mod 20, right? So we're right. I'm not sure what the proper context, proper generalization is for thinking about this, but did I say this right? GL1 of Z mod 20 is equal to, the congruence classes. Am I saying this right? 1, 3, 7, 9. These are the only ones that are relatively prime to 20.
Looks right.
And so this general linear group also functions as the Galois group of this field. And that's, there's some very sensible pattern there that this is just a special case of. But we're taking a very example-oriented approach. So I don't really have to try to figure out exactly what the general story is for when does this happen, how does it happen, etc. So, and you can sort of see what that what the structure of that GL1 is. Well, right, there's a Chinese remainder theorem type thing going on, right? That you can, 20 is equal to 4 times 5. Those are relatively prime to each other. So you can think of it actually as GL1 comma Z mod 4 times GL1 comma Z mod 5. And so we can draw that something like what? Something like, here we've got the prime 2 and it's the second power, and the congruence classes are 1 and 3. And here you have the prime 5 and it's just to the first power. And then the congruence classes relatively prime to 5 are 1, 2, 4, 3. And I probably listed that order because it's just convenient having, an element like 2 that generates this cyclic group. All of these multiplicative groups, all these GL1s for prime things are just cyclic groups. That's a very basic fact. So, this is a little picture of this GL1 and equivalently of this Galois group. And so they can just, visually pick out all of the subgroups.
Yeah, I think you're using this example in some old notes that I have, practically when you're talking about art and reciprocity or something.
Yes.
Yeah.
Yes. Yes.
So there were no abelian varieties or elliptic curves in our conversation back then. But
there may secretly have been.
Well, sure, secretly.
What year? Can you tell me what year? Can you guess what year it was? And I'll try to guess whether I was secretly trying to tell you about abelian varieties or not.
Well, I forget, it's a long time ago. But if you're secretly trying to tell me about it, you're sure keeping it secret because you were talking very explicitly about. I thought you were trying to understand art and reciprocity.
Yes, but art and reciprocity is very closely related to the Jugendtraum. And Jugendtraum has a whole lot to do with.
Yeah. So I don't know. You might have started. Yeah, you did at some point say some Jugendtraumish stuff. But anyway, so this is like a return of an old friend.
Yes, that's right. So let's try to draw a little picture of the subgroups. And yes, it is an old friend. I've drawn this picture so many times that hopefully I can draw it fairly quickly. Let's see. The Galois correspondence is contravariant. Big subgroups correspond to little subfields and vice versa. So that's a guide to getting the picture to work. So we have let's see. Smallest subgroup corresponds to the biggest field. Biggest subgroup corresponds to the smallest field. Now there's this subgroup over here. By the way, when I see this picture, I probably always have the temptation to think that this is like the corners of a cube or something like that.
Is it?
And I don't think so. I mean, no, but there may be. I'm not sure what it is, the corners of.
Okay.
Yeah, it's really not the corners of a cube. In particular, there's let me draw the POSEC structure. So the thing at the top really is the top. It really does. So the thing at the top is the octic extension, right? The 20th cyclotomic field is an octic extension of the rationals. And the next row down is the quartic extensions of the rationals. Next row down is the quadratic extensions of the rationals. And the next row down is the rationals. And, these are just all the things that fit inside of the 20th cyclotomic field. So, yeah, so it turns out that right, the thing at the bottom is in fact contained in all the quadratic extensions. But the next, the connections between top and bottom are a little bit unexpected if you're not expecting them. So what it is that the middle thing in the quartic row is very busy, and the middle thing in the quadratic row is very busy. So the middle thing in the quadratic row is actually contained in all of the quartics. So it's like this. And the middle thing in the quartic row is also very busy. It contains all the quadratics. So it's like this. Mm-hmm. So I think that's the POSEC structure.
Uh-huh.
And this makes sense, if you just think that we're just giving the POSEC of subgroups of this abelian group. It's just Z mod 2 Cartesian product Z mod 4. And so it's got like, it's got like, for example, this quadratic extension corresponding to that index 2 subgroup. I guess the other index 2 subgroup is this slightly peculiar one. Mm-hmm. So one of the things that makes this picture kind of fun is that every little corner in this picture has its own individual personality and flavor. And they're all good for something. Some of them are more famous than others, but they're all good for something. So if you look at those 3 index 2 subgroups corresponding to quadratic extensions, the one on the left and the one on the right are cyclic groups, cyclic subgroups. But the one in the middle is a Klein 4 subgroup. And that's why it's so busy in terms of having a lot of subgroups. It has 3 subgroups. So this index 4 subgroup is also very busy. It's contained in all those. Did I do that right? Yeah, that looks.
Yep.
Yeah. Okay. Whereas there are these other ones. Sorry. There's this one, and there's this one. And so one of the patterns that's going on here is, well, let's see. So let's try to, well, so first of all, we're taking the attitude here that we're sort of leading with the subgroups to get an understanding of the subfields, because, right, it's very easy to have a very direct understanding of the subgroups. It's just a finite abelian group, and you just easily see, yep, as we're drawing them, all of these subgroups. But it's, the subfields are more mysterious, but we can make them less mysterious by figuring out what quantities actually generate, what numbers actually generate these number fields. And, so we know that our favorite primitive 20th root of unity generates the thing at the top.
Mhm.
Now, this thing over here, this field over here, and this field over here are also cyclotomic fields.
Mhm.
This one over here is the fourth cyclotomic field. Again, I'm blurring together the subgroups and the subfields. I'm drawing the subgroups, but I'm talking about the subfields that they correspond to in the Galois correspondence. So,
And the other one is the fifth.
yes, and one of the visual patterns here, right, is that the fourth one is all column.
Yeah.
The fifth one is all row. Which I don't know, somehow that makes sense, right? I mean, what is it? Our horizontal dimension corresponding to the prime 2 and our vertical dimension corresponding to the prime 5. So why is it like that? I don't know. I guess it's like, I guess that's the 2, let's see. I guess that's the 5 axis that gives you the fifth cyclotomic field. And the 2 axis, am I saying that right? Yeah, the 2 axis is giving us the fourth cyclotomic field. Just in the sense that, where was it? Did I erase the picture? Where did it go? Oh, it's over here. Yeah. I mean, it's also, right, it's just the usual confusion, right? On two-dimensional graph paper, what's the confusing thing? That the x-axis is
where the y is equal to 0, and the y-axis is where x is equal to 0.
How can that be true? Did I get it backwards?
No, that's true. It's when you go to 3 dimensions, then you see the pattern. Yeah, I mean, it was.
Well, so I did
that because you said the 5 axis, and it was.
Yeah, I think I got something.
It looked like the 2 axis, but it was, I think, anyway, I know what you're.
Yeah, I mean, I think I did get it backwards, but if I didn't get it backwards then I'm probably getting it backwards now. So it probably will evens out. So.
Okay.
So those are important landmarks in this Galois correspondence. Those are those other cyclotomic fields. So I guess what we're saying that a generator here is 1 to the 1/5, and the generator here is 1 to the 1/4.
Yep.
So you could also say this is the Gaussian rationals over here. In the quadratic extension row on the far left side, it's the Gaussian rationals, or if we take the algebraic integers inside there, then it's the Gaussian integers. On the quartic row, the far right is the fifth cyclotomic field. So that's kind of where the pentagon or pentagram or something lives. And let's see. So let's see. Over here is the other 2 quadratic extensions. One of them is 5, generated by 5 to the 1/2. And the other one is generated by -5 to the 1/2. So the one that's generated by 5 to the 1/2, that's the very busy one. If you think about it, you can see why that's the busy one. So, I mean, right, 5 to the 1/2, that's not the golden number itself, but if you take its average with 1, that is the goal, right? 5 to the 1/2 is the square root of 5, it's about 2.2 or something like that. You average that with 1, it's around 1.6. So that's the golden ratio, the average of, right. So part of the point is that the square root of 5 generates this quadratic field as a field, but it doesn't quite generate it as a ring. You need the golden ratio or something if you want to get those. Sometimes it's slightly unexpected what all the algebraic integers are. Sometimes they're more than you might have guessed at first, and that's this golden field is a classic case of that. So there's probably some theorem that says you can generate any of these fields with a single element, but I don't need to do that. I can just say that this very busy quartic is generated by any two of the quadratics, right? So I can say that it's generated by 1 to the 1/4 and 5 to the 1/2 or something like that. Okay, so we've almost nailed down the personality of all these fields in some sense, or the personality, the personal history. Right?
How are you going to do the, except for one. So what do you do for the upper, sort of upper leftish one?
Yeah, the leftmost one in the quartic row. I ought to be able to tell you exactly what would be a good generating element of that. It annoys me that I can't tell you right offhand what number is there. I can tell you that if you read Ramanujan's first letter to Hardy, it's discussed in there. So this,
well, okay.
That's part of what I mean when I say that everything in this picture has some interesting history to it. So I think that there's something in Ramanujan's letter to Hardy that's actually, and I didn't find that out until a long time after I'd been drawing this picture. That leftmost thing in the quartic row was always, slightly mysterious to me. And then at some point I found out that it was the subject matter of one of Ramanujan's famous problems or something like that. So that would be fun to find out what the hell Ramanujan was doing with that. But we can at least say, there is one thing we can say about this field, even if I can't instantly tell you a generator for it. I can tell you that the generator for it looks a lot, when you squint at it the right way, it looks like a mutant version of the generator for the rightmost one on the quartic row, thinking of both of them as extensions of the golden field. They're both extensions of the golden field, and they have like almost the same minimal quadratic polynomial, except one of them has like an extra minus sign in it or something like that.
What do you get if you do the square root of 5 together with I? What if you generate
that's the busy one in the quartic row. That's the
oh yeah, sorry. Yeah.
And that's also what you get if you take the square root of 5 and the square root of -5, or you just take the square root of -5 and the square root of -1. The way I said it was that any two of the quadratics give you that busy one.
Yeah. Okay.
And I guess that has something to do with the fact that there we've got a quotient group that is a Klein 4, I guess.
More and more curious about this missing one. I think you're trying to force me to like read Hardy's letter to Ramanujan just to figure out very inefficiently what this.
Well, I think I can give you a somewhat satisfying answer, but it doesn't. But not by a generator. Like I say, it really is easy to come up with a generator, but I'll bog us down if I try to do that right now. But one thing you can say about it is that it's the real part of the 20th cyclotomic field.
Okay.
So, right, look at that little element right there. Oh, well, so first of all, let's just work out how does the Chinese remainder theorem work for 20 equals 4 times 5? So what is it? 1 is 1 mod 4 and also 1 mod 5. But what, 11 is 3 mod 4 and 1 mod 5? Can you help me out with the rest of these? Is it like 17? I mean, I just did this. I'm a little bit in practice now because of, I think it's 17 and 7 maybe. Does that work? Yeah, 7 is 3.
For me, it's an NP complete problem. I can verify them, but I can't.
Okay, let's do it that way. So I think it's going to be, yeah, right. I'm hoping that should be a 19 right there, because 1 to the 19/20ths is the complex conjugate of 1 to the 1/20th. So I think it's going to be like 9 in there, and maybe 13 there, and 3. Okay, that was all guesses, but does it look right?
I'm going through them. It's, so far they're looking right.
Yeah.
Yeah.
I think that's right.
Yeah.
So in particular, right, that one that I circled over here.
I only need to check all but one of them. So.
Right. It's probably, I'll bet there's a more efficient way than that.
Yeah. I'm sure there's
But right, I was saying that's 19. So that's the element of the Galois group of the 20th cyclotomic field that takes the primitive.
Oh, okay. So I think you're telling me I can just use 1 to the 1/20th plus 1 to the 19/20ths.
Yes, but that sounds yes, that's true. Okay. Yeah, yes, that's true. That's true. You can just take the average of those two, or the sum or something like that. But I think if you read Ramanujan's letter, then what I think it has more to do with expressing that as a quadratic extension of the golden field. So there's just, a quadratic polynomial with coefficients in the golden field that has that thing that you're talking about as its root. And that's what I was cavilling at or whatever.
Yeah.
But yeah. So yes, you're probably right about that. But in particular, in some sense, you can think of this as the real part of the 20th cyclotomic field. It's the things that are their own complex conjugates. I mean, to what extent does it even make sense to ask for the real part of this? Well, I think it does make sense in this case, but I'm not sure if I could explain exactly why it does make sense, but it makes reasonable sense in this case.
This is a constructible polygon, this 20gon. So
it's just as constructible as the pentagon, right? You don't have to do it. I mean, once you
you just bisect.
Yes. Yes. Now you're also making me want to think about the abelian variety coming from Gauss's 17gon, the 17th cyclotomic polynomial. That would give us a what? An 8 complex dimensional abelian variety? I guess I shouldn't think about that right now, but you
haven't even
forced me to think about that.
Get the abelian varieties yet.
Well, I mean,
I'm supposed to know right away.
Well, did I understand what you said? I mean, what we're going to do is the vague idea is we're going to use the ring of algebraic integers in any of these things, or some of these things at least. We're going to use those as period lattices, roughly. I mean, some people think of it in a slightly different way, but that's the way I'm thinking of it. We're going to use these number rings, the lattice versions of these things, as period lattices, which in order to get that to work, we need to think of the ambient background that they're living in as being complex in order to get complex abelian varieties out of this. So, right, so naively, this one that we were just talking about, the quadratic extension at the furthest left, that looks like it's not that useful for getting us a complex abelian variety, but it may actually be helpful for understanding other complex abelian varieties in this picture. I mean, again, we're going to try to extract from this picture as many useful, entertaining abelian varieties as we can, and learn about them. We're going to learn about their complex multiplication phenomenons. I mean, we're absolutely getting, to the extent that we're getting abelian varieties at all, we're getting ones that have complex multiplication. But I'm really interested in, the Néron-Savary groups of these. And I'm also very interested in the thing that you were talking about earlier today and last week about motives. I want to count points of these abelian varieties over finite fields and do stuff like that. And maybe
By the way, this
yeah,
that little stuff I was talking about at the beginning,
yeah,
I left out all the part about algebraic integers, which is hiding in there, partially because I'm not just like confused about some specific fact and getting some kind of contradiction. But those, if I'm not too confused, and I may be confused, that number I was calling alpha, part of the vague hypotheses conjecture said that that's an algebraic integer.
That sounds vaguely familiar. That it's an
and
algebraic integer. Yeah.
And so I was.
Did you were you hinting at that already? Maybe you were.
I mentioned it in my talk. Well, I don't know. I told you last time something about that.
Well, I thought something you said today might have hinted at it, but I don't know.
So
yeah.
So there, we're getting algebraic. We're just like trying to count points on an elliptic curve, and we wind up getting these algebraic integers showing up. So that's sort of maybe that's like coming at this from the back end or something like that.
Yeah, I don't know what to make of that yet,
but algebraic integers, or these, well, algebraic numbers at least.
Yeah, I mean, it's very suggestive, but I'm not sure what to make of it yet.
Yeah.
So yeah, I mean, some of our abelian varieties actually will be elliptic curves. So those will be curves already. So we could play some of the kind of games that you were playing with curves. But there are other abelian varieties in this picture, hidden in this picture, that may be Jacobians of other curves. So there may be, other curves hidden in this picture as well. And the Jacobians of those curves may have something to do with certain motives of those curves. I don't know. We'll see. We'll see as soon as I start learning what a motive really is. So yeah, so that quartic on the far left is not that mysterious. I'm still curious what Ramanujan was doing with it, though. Well, so let's start thinking about where in here maybe we have some abelian varieties. And again, I have a feeling that I have a feeling that I'm doing some very lowbrow version of something that there must be very highbrow versions of. So for example, I look at the quadratic extension row, and clearly this one here is real quadratic field, real quadratic number field, but the other two are imaginary quadratic number fields. So I know how to interpret those imaginary quadratic number fields, or the algebraic integer lattices in them. I know how to interpret those as period lattices for elliptic curves. So we're looking at two elliptic curves there.
Yep.
And perhaps the one at the left, maybe it's called Gauss's lemniscate, associated with the Gaussian integers, but don't even trust me on that, because I get really confused by different terminologies here. So the one on the right has fairly skinny rectangles as its fundamental regions. They're not exactly golden rectangles, but they are rectangles of some kind. And then there's, well, there are certain other games. There's another elliptic curve hidden in here that's going to show up at some point, but we don't have to talk about that yet. Well, it has to do with the ideal class group, because ideals in this number ring also can give us things that we can interpret as period lattices.
Uh-huh.
There's actually a non-trivial ideal class in this
Right.
imaginary quadratic over on the right. And that's
That's one
probably
of those famous stories as well.
yes, yes, there should be fun stuff there as well. So far it just looks like there's two elliptic curves. Well, perhaps three if you count that other one I was mentioning. But there are two that are staring at us in the picture. See, somehow I'm like circling the ones here that are complex extensions, but I don't even know what it means really for these to be complex extensions. But I mean, people talk about totally complex fields and totally imaginary fields. No, totally imaginary fields and totally real fields or something like that. I have a feeling that this one here, I'm circling the ones that don't look like they're completely real, that are the ones that are just made out of real quantities. So the golden field is very real, doesn't really have any imaginary stuff in it. And that quartic on the left is very real. You know, it's the real part. So, so it looks like there are two blatant complex abelian surfaces that are just circled in the quartic row.
How systematic is it to think of these two on this row that you're talking about now, to think of them as giving you lattices in a two-dimensional complex vector space? That is, where do you get that two-dimensional complex vector space from?
Yeah, that's very embarrassing that I can't tell you how systematic it is. I mean, presumably there's a very systematic theory of this, and I'm totally faking it at this point. I mean, down at the quadratic level, I can just, just kind of fake it.
Yeah, there you can
without any problem.
Yeah, even then you're sort of.
Yeah, even then you're
sort of faking it as.
Right, there's some Galois ambiguity, but that seems harmless.
Right.
And then as you go up in the quartic row, it seems less harmless, but you try to get by anyway. And there's some very systematic theory of this that other people know, but you're asking the wrong person. So I'm going to be faking this a lot.
Okay, so
yeah.
So I vaguely remember.
Yeah.
The Minkowski's geometry of numbers was like not just ways of getting lattices from quadratic number fields, but getting lattices from a bunch of whatever you call them, higher degree number fields, getting lattices in complex vector spaces and using the geometry of those. But I guess I never understood. Whatever I understood seems to have evaporated except for the quadratic case.
Okay. I have some vague ideas about that, but yeah, I don't have anything very precise about that either. But it seems like, something we can try to fake for now, but maybe we might have to actually learn some of that at some point.
Okay.
And then there's this octic one here that looks like it's also probably going to give us a complex four-dimensional abelian variety, I think. And well, so let's look at the quartic row, okay? Let's look at the quartic row. So in the quartic row, we have the thing in the middle with the two generators. And just naively, that looks like, that's just going to be a complex abelian surface. That's a Cartesian product of two different elliptic curves. So that one seems like it should be pretty easy to understand, just because it's a Cartesian product of elliptic curves. And by the way, if you take the one that's a non-trivial ideal over that, then that should also be fun. A little bit more complicated, but.
Sorry, which one? Oh, I see. Yeah. No.
Yeah.
Yeah.
Yeah. Right. That one with the non-trivial ideal, that looks like it's going to be isogenous to a product of elliptic curves or something like that.
Right.
But I don't know. Maybe they all are. I don't know. For the abelian surfaces, I don't know. Let's see. Or maybe they're not all that way.
I don't think so.
Okay, I don't.
That would make life too easy. Yeah, I don't know.
Yeah, I don't. I don't know. I just remembering vague things. I heard about some of these things. So the rightmost in the quadratic one, that's one that we've already started talking about. That's one we've already started talking about. I think we started drawing some pictures of this like a couple of weeks ago or something like that. So in fact, let me well, and again, so notice that notice that this golden field, which is purely real, the golden field, which is purely real, is contained in this fifth cyclotomic thing. And it's tempting to try to think of the fifth cyclotomic thing as, in some sense, just being the complexification of the golden field when we visualize it. And I have some vague plans about, trying to exploit naive visual intuition along those lines. When we try to figure out what the polarization, right? That's one of the big things we're trying to understand. We're trying to figure out the polarizations on all of the abelian varieties that we're trying to extract from this, right? One of my big annoyances, I don't really understand these neuron severity groups very generally yet. And this seems like it should be a good bunch of examples to try to understand the neuron severity groups. And yeah, there's a whole bunch of examples to play with here, examples of abelian varieties to play with. I really want to understand their neuron severity groups in many different ways. For example, you tried to teach me something about sort of Jordan algebraic approach, trying to remember some of the buzzwords, Jordan cone and self-adjoint, Rosati involution. Yes. So all that stuff should be the kind of thing that we should be able to experiment with very concretely with all of these examples. So at some very naive level, it's tempting for me to try to picture the fifth cyclotomic field as living in the complexification of the real vector space where the golden integers live. And that this might help us to visualize the polarizations, so there's that whole space-time Lorentzian cone, Jordan cone thing. Anyway, we're going to try to visualize all of that. Visualize and or calculate it with it, understand it in any way we can. So, and we could do the same thing perhaps with the real part of the 20th cyclotomic field. Maybe I have some very naive guess that says something like, maybe what you should really do is you should find these totally real fields, like the golden field or that other very real one. And then you should complexify them in some sense to get totally complex number fields. And maybe, I don't know. But I think the Jugendtraum, the generalized Jugendtraum, as it's been developed so far, is mostly based on totally complex, totally imaginary number fields, whatever those are. I think it's rough. I'm guessing that the ones we've circled maybe are totally imaginary. You can't fit them inside the reals or any product of the reals, I think. They're intrinsically very complex. I'm not sure I'm using the right definition or the right concept of totally imaginary or whatever, but we're faking it as usual. So, so what am I trying to say here? So,
sorry, I gotta answer.
Go ahead. This will give me time to think. Maybe it'll give me time to think, but it won't give me the power to think. Let's.
Okay, drunk.
Okay. Oh, okay. So I think what I meant to say next, I'm trying to get to another notebook here if I can find it. Yeah. So this is a picture from my notebook with Simon. Let me try to enlarge the picture a bit. How do you, where's the zoom? Zoom is like
That should be it.
positive. Maybe that'll be good enough. So this is some mysterious picture that I started drawing. That it started out as a picture of the golden field. But it started as a picture of the golden field, but then partially for reasons that you and I discussed a couple of weeks ago, somehow in the visual picture of it, some 90-degree rotational symmetry emerged. And at some very naive level, that made me think, oh, maybe there's some secret mysterious relationship between the Gaussian field, which is secretly all about 90-degree rotations, and the golden field. So let's just stare at this picture a little bit, try to soak up the visual intuition of how this is a picture of the golden integers. Now, I'm not at all convinced this is the best way to draw this particular field. I started drawing it at random. I decided, I mean, maybe it's not surprising that I ended up getting 90-degree angles out of this, because I just randomly decided to draw the golden ratio at the point that was 90 degrees away from 1 or something like that. I think I'm using the color gold for the golden ratio. We'll try to interpret that picture, but well, so like one, right? Okay, I mean, right. One of the first questions you can ask about this field, well, first of all, think of it as a number ring. So, well, and I mean, we said as a field, it's generated by the square root of 5, but yes, and as a number ring, that's not good enough. You have to take the average of the square root of 5 and 1, and that's called the golden ratio, and that is the generator as a ring. So it kind of as a lattice, that's kind of generating this lattice. So you can see the fat black thing, fat black dot in the middle, that's kind of the origin, that's 0. And how well can I interpret my own picture? I think, the graph paper is supposed to be, right? The integer 1 is just supposed to be 1 grid step to the right of that. And then for some strange reason, right, I drew the golden ratio as 1 grid step below the origin. And I guess at that point, one of the things I tried to figure out was, what is GL1? What is GL1 of this number ring? And I have a sort of guess, and that's what this picture is sort of showing. So again, I have a feeling that this might be secretly something that's in the history of mathematics. This might be called the Pell equation or something. Is that true? Studying the multiplicative units, multiplicatively invertible elements in these real quadratic number rings. And so, I mean, so you can see these points.
So it looks like you're taking powers of G and getting all the golden stuff. Is that what that is, or is it?
I think the color scheme is a little bit more disorganized than that. I mean, so right. I mean, this if you tensor with the reals, it becomes the reals squared. But the axes for that are not the original axes of the graph paper. Right, I mean, can you, okay, let me try to act this out a little bit. So again, here is the golden ratio. But I tried projecting it onto its numerical values. So like, if I project it over here, that's where it takes on the value negative 0.6 something.
Yep.
And if I project it over here, then that's where it takes on the 1.6. Is that right? Does that look? It's hard to tell, but yeah, I think that's right. I think that's right. And see, that sort of gave, right, this superimposed grid, which I sort of drew in black. I drew these axes. You know, those are the two different fields that are the semi-simple. Those are the simple factors of this semi-simple thing after you tensor with the reals.
Uh-huh.
And
so there are two square roots of 1, which are 1 and something else.
well, there are 4 square roots of 1. That's right. There's 1, 1 comma 1, 1 comma negative 1.
Yeah.
So there's 4 quadrants. You can sort of see the 4 quadrants relative to this black little pair of axes. And you can see 1 is in the, is that what we call the first quadrant? Yeah, the first quadrant is where 1 lives by definition. And then the golden ratio lives in a quadrant next to that because, right, in one of the factors, it becomes a negative number and the other one becomes a positive number. So it must be in, it's probably just a matter of convention as to whether it's in second quadrant or fourth quadrant. Is that right?
Yeah, since you do everything upside down.
Okay, so if you start taking its powers, I think it's going to go through all the quadrants. But it's always going to lie on these Fibonacci hyperbolas.
Mm-hmm.
So yeah, I think what's going on here, okay, this, I'm taking this as usual, but it seems to me that GL1 here is probably the direct sum of Z mod 2 and Z. And, you know, the Z mod 2 is just the powers of -1. And the Z is the powers of the golden ratio. And, you know, the Z is in this quadrant that's 1 away from the main quadrant. So it just, as you take its powers, it cycles through all the quadrants. But, you know, if you include all the negatives, then you're filling out all these. I mean, right, it's sort of like there are 2 Fibonacci hyperbolas here. But, and the reason there's, I mean, each hyperbola has its 2 branches. But then we have, you know, the 90-degree rotation of that, which is, there's other 2 branches. And that's because, am I doing this right? Let's see. Something like
G squared in this picture.
All right, where's G squared? G squared is 1 plus G.
Yeah, okay. I guess I could have figured it out. So it's that red dot to the left of, to the right of the big golden dot.
Yeah, so I was probably wrong when I said that it just cycles through all the quadrants. That's probably not quite the right thing to say. Or is it? I don't know, but somehow, for some strange reason, it accounts for this whole 90-degree rotation.
Sorry, what accounts for it? Just the powers of G? No. Yes.
I think what I'm saying is that all of the multiplicatively invertible elements are, on the one hand, the powers of G, and on the other hand, all the negatives of the powers of G.
Mm-hmm.
And you could also say something like all the powers of G, all the powers of the other root of that equation. But that still doesn't account for all of them. They're right. They're the ones that are the ones that are negative in both, right? The ones that are in the third quadrant or something like that. Those are the ones that are neither powers of the golden ratio nor powers of the other group, but they're negatives of powers of both of them. So yeah, so one of these quadrants has things that are powers of the golden ratio. The other one has things that are powers of the other one.
So the
The other
powers of the
quadrant-
golden ratio are going down and to the right. Is that correct?
Say that again?
As you take higher powers of the golden ratio, you keep moving down and to the right in this picture, I think. Does that sound right?
And that's all that ever happened?
It looks like you keep sort of zigzagging back and forth, hopping between the two branches of the hyperbola. The branches of the two different hyperbolas. So
I guess that's right. But then when you start taking negative powers of the, what happens when you start taking negative powers of the golden ratio? They go into some other quadrants or something like that.
yeah, so you have -1 plus g. So that's the green dot.
Yeah. And you never get something with both the g coordinate and the 1 coordinate being both negative, unless you deliberately take the negative of right. But I mean, that's what I'm saying. Like, -1 also contributes to the
Yeah.
to
right.
TL1 here or something
Mhm.
like that. So
Okay.
like I'm saying, we're supposed to soak up whatever visual intuition is in this. Again, this isn't really a period lattice of an abelian variety because this is living in a real thing, but it may have some auxiliary use when we're trying to understand this complex abelian surface. So who knows? I mean, it's also possible that I soaked up some of the wrong intuition from this. So again, I started staring at this picture. Well, right. I mean, this picture was very arbitrary. There are other angles that you could have the axes at, and those might be better, more conceptual or something like that. There's all sorts of different ways you could draw this picture. This way of drawing it is suggestive of 90-degree angles, but maybe that's completely the wrong intuition. But regardless of whether it's the wrong intuition or not, it encouraged me to enlarge my thinking to include the whole 20th cyclotomic field, because that also has the Gaussian integers as well as the golden integer in it. So, maybe there is some funny higher dimensional picture staring at me here that's really telling me about the mixture of the golden integers and the Gaussian integers, or maybe not. But this is what we're doing. This is what we're doing. We're trying to understand all these Gaussian integers and golden integers, get all sorts of abelian varieties we can from this, and learn whatever we can from this. So, all right. So let me go back to our main notes page, if I can find where it is. Okay. So well, so there are all sorts of things that I want to try here. In some sense, the main plan is to try to calculate the Néron-Savary groups of some of these abelian varieties by thinking in terms of Rosati involutions or polarizations or whatever. Mm-hmm. But I think I'm not really going to start on that today. I think instead I'm going to just start thinking about playing around with counting some finite points on some of these abelian varieties. There's counting points on finite fields and stuff like that.
Counting points on
counting points over finite fields on some of these abelian varieties. And we'll start with a very simple case. We'll start with the Gaussian, the period letters coming from the Gaussian integers, okay?
Okay.
Start with that example. Start with that example. I mean, and as usual, we're aiming to quit roughly, approximately, pretty close to 6:30 p.m. today.
Yep.
So we still have 20 minutes left. So the part of the intent here is to converge what I'm trying to do right now with some of the pictures that you were just showing last week and today.
Uh-huh.
So you were kind of showing us some tables, basically counting points over finite fields
Mm-hmm.
for certain elliptic curves. And I have a certain elliptic curve here, and I'm doing the same thing. So mine is probably going to be something like, I mean, this one here, it's going to be something like, sorry, I don't want that color. Let me, yeah, that's the golden color. I don't want that. Sorry, why is this? This doesn't look the way I want it. Is this the right thing? How does this work? Let's try that. Ah, no, that's not it.
What?
Share. No, I didn't want that. Okay, how do I turn that? Okay, so maybe it's this.
I was
Oh,
trying to watch some string theory YouTube videos, and
yes.
both of them started with about 15 minutes of somebody trying to get their computer to work.
Yes, yes.
All these super smart string theory.
Well, I'm no better. I can't claim to be as smart as them, but I'm at least as bad at the computer stuff. So,
I think you're better. I'll show you. I was reading this video on geometric Langlands. Like the first 20 minutes is just like, I can't share my screen.
well, but it's
Yeah.
so easy to sympathize.
Yeah, I don't. But anyway, yeah, I sympathize more with you.
Well, it's easier to sympathize with it happening. It's not necessarily easy to sympathize with not being able to edit it out or something like that.
Right, yeah. Okay, I'm dying to know what you're gonna do next, because I would, if I were trying to count points over a finite field of the Gaussian elliptic curve, I would need to remember or cook up an equation for it, like an like a Baez, whatever you call it, Baez transform, like one of those kind of.
Sure, something like that. I'm gonna fake that. It's this Gaussian example is so easy that I could probably just fake it. If you force me to do this other one on the rightmost side of the quadratic level, I would probably trip over that one, and you'd watch me, try it for 20 minutes, and then I wouldn't come up with it. But this one I can fake. This one I can fake, the Gaussian integers. It's just going to be something like, I mean, there's all sorts of ways to think about it. I often tend to think of it as something like y squared equals, don't tell me, x squared plus 1 over x squared minus 1, or something like that. Because, somehow that, I hope I'm doing this right. I mean, I'm going by vague memories of having worked this out, and I'm not sure how close to the standard way I'm doing it, but I have a feeling that this is probably not too far incorrect. I mean, right, I'm just kind of, my right-hand side is some function of x, and it has, what do you call these? Well, zeros or infinities, I guess. What do we call those? Zeros and poles or something, I guess.
Yep.
So it has basically 2 zeros and 2 poles, and they're arranged in a very square-like fashion. So this is like the zeros and poles here are at 4 equally spaced points along the equator of the Riemann sphere or something like that.
Uh-huh.
So, I'm just writing this in some very sloppy way involving rational functions. We may want to homogenize this, et cetera, et cetera, et cetera, et cetera. But at this point, we're just kind of faking it. And let's see, how non-annoying and or annoying would it be dealing with that fraction bar when we're working over a finite field? I mean, you just have to be careful about division by 0.
Yeah, I was thinking how it's a little weird over the
Yeah.
field of 2 elements.
Yeah, but
I don't know if that's, I don't know much about this stuff, so I don't know if that's.
well, you're hinting. One of the things you're hinting at is that this field is like ramified over the prime 2.
Okay, yeah.
Well, at some point, we'll have to figure out what it means for something to be ramified over the prime 2. There are very lowbrow ways of thinking about it and very highbrow ways of thinking about it, but we're running out of time even for the lowbrow ways at this point. And like when you were doing this thing with your elliptic curve that you somehow plucked out of thin air or caught out of thin air, you were being pretty sloppy too. Like as an afterthought, you pointed out, oh yes, I wasn't including the point at infinity or something, so my counts were actually off by 1, which was okay because it was actually connecting with something about that very special trivial term in the
Counterpoint, yeah.
yeah.
0 term, yeah.
Yeah. So I'm probably being at least equally sloppy here. So right. Right. So what would be much better is if I could now immediately turn the tables, and just like you handed me a little table, if I could turn the tables and hand you a table for this elliptic curve. And I was actually working on that. I didn't quite get it. I don't actually have the table of numbers here. But
Are you doing it over some particular finite field or what? Lots of finite fields?
I think we're going to sort of try it over all finite fields. So what?
Okay.
So what were you doing? You were doing it over all finite fields of a particular characteristic or something. Is that what you were doing, or were you kind of doing it all?
Yeah,
fields?
just powers of 2.
Okay. Well, okay. I'm not sure what I'm doing here. We'll see how it goes here. But yeah, it could be that I'll mostly be focusing away from powers of 2 because of this.
Yeah.
I mean, this field is ramified at the prime 2. I mean, all quadratic fields. Is that right? Is that true? No, I'm not sure. I can't even guarantee that. I mean, ramified turns out, has different meanings for fields and for abelian varieties. So I don't even know what I barely even know on a good day what ramification means. So I'm a little bit confused about what is going on here. But let's see. So what am I trying to say? So, okay, for one thing, I'm going to dig up my little computer here and try to cheat by referring to some emails from when I was corresponding with somebody about this stuff. And so let's see. So, see, there can be some really neat patterns in these tables. I mean, it might end up that you'll have to take my word for these, patterns. We may not see them today, but we're really going to see them. But at the moment, it's feeling to me like the patterns that I'm trying to show you feel a little bit orthogonal to the patterns that you're trying to show me. So I'm very interested in learning about the patterns that you're trying to show me. How to do these motives and stuff like that. The patterns that I'm kind of trying to show you here have a lot to do with complex multiplication and the Jugendtraum. It's kind of the whole point of the Jugendtraum, as I understand it. How the Jugendtraum connects with the art and reciprocity and stuff like that. So I'm struggling to show you what's going on here in that these patterns that we should be able to. So, okay. So first of all, I'm going to try to move down the page a little bit. And at the moment, we're just going to think about the Gaussian integers and using the Gaussian integers as a period lattice to get an elliptic curve. I don't like that color. It's green. Let's go to black or something like that. So this is just an origin of my period lattice or something like that. Let's see. I guess I don't have to. Right, I guess right. I guess this is the grid is already pre-drawn. It's just the graph paper.
Yeah.
This is the lattice is the grid intersection points, grid crossing points of this graph paper.
That's
So-
why Gauss started with the Gaussian integers.
Say it again.
That's why Gauss studied the Gaussian integers.
I'll have to think about that. I mean, maybe that's obvious, but so
I don't know if they had graph paper for sale.
I mean, there's all sorts of mysterious connections to least squares and stuff going on here. But so what am I trying to say here? That I mean, so the elliptic curve is just wrapping up or modding out by this period lattice. And I mean, in some sense, the whole Jugendtraum is just about staring at graph paper like this, except it may be, more oblique graph paper or something like that. Staring at the piece of graph paper and thinking about it as the picture of two different things. Thinking about it as the picture of an abelian variety, an elliptic curve on the one hand, and on the other hand, thinking of it as the picture of a number ring. So it has to be the kind of grid that you can think of as an imaginary number ring, a totally imaginary number ring or something like that. So we'll have to haggle about what that means. But so what is that supposed to mean? What is that supposed to mean? What are you supposed to learn by staring at this graph paper and thinking of it as being simultaneously two different pictures? So what it really means, I think, or my best approximation so far to what it means. And we're really gonna have to try to, learn more about this and understand what it really means. But my first approximation is that there are certain group actions going on here that start out seeming rather different and disparate to each other, and they end up being secretly very cryptomorphic to each other. And now you've got me wondering whether it's really just some elaboration of the thing we already ran into, where the GL1 of Z mod 20 turned out to be the Galois group of the 20th cyclotomic field. Maybe it all secretly is just like that, but let's see if we can get something going here. So, and again, I'm trying to cheat here, my last 10 minutes with things going here. So what am I trying to say? Okay, let me try to read. Let's see, is there some way? How can I do this? Again, if I were technically competent enough, I would just be displaying my email up on the screen at the moment, but I'm sort of running out of time here. I'm going to just read it out loud here.
Sure.
It says, thus, for example, let K, actually, let me go one paragraph before that. It says, as I understand it, Kroneker's Jugendtraum has in part to do, what is this date from? This is from 2015. So I'm trying to pretend that this email was written by me. I mean, it was, but me in 2015. So it says, as I understand it, Kroneker's Jugendtraum has in part to do with generating abelian extensions of a quadratic number field K by coordinates of torsion points on an elliptic curve with complex multiplication by the integer ring of K. And I've been trying to understand this in particular examples, sometimes with the help of homegrown computer programs. And I've been seeing interesting patterns that I don't fully understand. Thus, for example, let K be the field of fractions of the ring R of Gaussian integers. Then Gauss's lemniscate is an elliptic curve with complex multiplication by that ring. And one manifestation is that, at least according to my tentative computer calculations, for a positive prime number P in Z, congruent to 1 mod 4, and a prime ideal J in R lying over the ideal generated by P, there's a unique generator G of J such that the abelian group of points of the lemniscate over Z mod P as a representation of the absolute abelian group, absolute abelian Galois group of K is isomorphic to the tautological representation of GL1. Okay. Okay. Sorry, I wish I.
You're much more erudite back then.
But the idea is so completely pictorial. But that's why I feel like I should be able to. I mean, you can't really, I don't think you can really understand this idea unless you make it really pictorial. I'm trying to make it pictorial. Let's see. So it says, okay, this is a picture of the Gaussian integers and it's a picture of Gauss's lemniscate. And it says, so, okay, it tells us, this email is telling us to think about the tautological representation of GL1 of some finite quotient ring of the Gaussian integers.
Mm-hmm.
So let me try to get some finite quotient ring of the Gaussian integers here. So let's try to mod out by this Gaussian integer right here. Now it's like 2 plus 3, or 2 minus 3 times I, or something like that. What is the quotient ring going to look like? I mean, so, okay, so this is going to generate an ideal. The whole ideal it generates is going to be something like this, and I'm drawing this correctly, this, and
yeah,
this.
Yep. So you get some lattice.
Yeah. So it's like, can we get a sense of how many, what's the size of that quotient ring? So, right, I mean, so, right, this is also saying that we have some sort of sublattice of our grid lattice. And so this is giving like a covering of our abelian variety by another abelian variety.
Mm-hmm.
So let's see. Let's see.
So you're also asking like, it's an n-fold cover for what n?
Yes,
That's
yes.
another way to ask your question.
But yeah, I mean, on the one hand, I have a sort of guess that says that it's 25. But do I really believe that there are 25 grid points inside that little square? With, you know, double half counting on the boundary or something like that?
Well, luckily the boundary doesn't hit any points, except
Okay.
well, you got to worry about the corners.
Right, so there's one. So right, so there should be 24 in the middle there. Does that sound at all plausible?
I would just count them.
All right, let me try. 1, 2, 3, 4, 5, 6, 7. Am I doing something wrong here? 7,
No, you're doing great.
9, 10, 11, 12. Oh, I guess that's 13. I guess there's 13, right? There's 12 inside, and that gives us a total of 13. And this makes sense because 13 is a prime of the 13 is congruent to 1 mod 4. I think this makes sense. So, okay, so that's a little quotient ring. It turns out this quotient ring is really just Z mod 13. But we have the, right, so GL1 of this little thing. GL1 of this little ring is like a 12 element abelian group, right? It's the multiplicative group of a this picture doesn't look like your standard picture of Z mod 13, but it really is Z mod 13. And so the multiplicative group is just the cyclic group with 12 elements. And you know, in this picture, there's sort of a tautological action of that group.
On what? On
I think I want to say on the elements of the quotient ring. We're really running out of time, so I'll really have to try to clarify this better the next time. But I want to say that it's something like that. It's something like the tautological representation of this GL1 on these points.
Mm-hmm. Okay.
And what that's supposed to be cryptomorphic to, and again, we'll have to say it better next time, but it's supposed to be something like the action of the absolute Galois group of the Gaussian integers. So the absolute abelian, well, even just the absolute Galois group, but it's only the absolute abelian part of the Galois group that's acting. Acting on these torsion points. So, right, I mean, these are particular complex numbers, or these are particular points on the lemniscate with particular coordinates that are complex numbers. But those are not just complex numbers, those are actually algebraic numbers, and they could be acted on by the Galois group, the absolute Galois group of the Gaussian integers. And so there will be a Galois ambiguity, Galois permutation symmetry acting on these torsion points.
You mean the Gaussian integers, or do you mean the Gaussian integers mod this ideal? Sorry, the Galois group of the Gaussian integers isn't all that big, right?
No, but I'm not talking about that. I'm talking about, when I say the absolute Galois group of the Gaussian integers, what I really mean is you take the Gaussian rationals, really, and you take its algebraic closure.
Okay.
That's a big,
yeah,
huge thing.
Uh-huh.
And that has a big Galois symmetry group. And that's, right, that's acting, right? This is like the analog of the absolute abelian group of the rationals, except we're not starting from the rationals, we're starting from the Gaussian rationals.
Okay, yeah. Sorry. Yeah.
That thing acts on algebraic points with coordinates of yeah, It acts on things like the points of this abelian variety. So we're out of time, but what I'm trying to say is that we're supposed to see how these two things, these two pictures that I'm very incompletely sketching for you so far, but they really are the same picture. One is a picture of the Gaussian integers. One is a picture of the lemniscate. And we're going to see that the action, a very visible action of GL1 of the number ring is going to secretly be the same thing as the action of this gigantic absolute abelian group of the Gaussian rationals acting on the points of the lemniscate. So we have the double interpretation of this picture. It's points of the lemniscate, and these things are little torsion points on the lemniscate. These are like order 13 torsion points. This is a 13 picture. This is sort of a picture of the 13 torsion of the lemniscate on one hand. On the other hand, it's a picture of this quotient ring, this order 13, order in some different sense, or in some same sense, order 13 quotient ring of the Gaussian integers. And these two pictures are going to blend together in a perfect way. But in one picture, it's going to be the action of the GL1. In the other picture, it's going to be the action of the abelian group, or the action of the absolute abelian Galois group. And
you get the action, you get the Galois group, the absolute Galois group of the Gaussians mod. It seems like there should be some much smaller group than the absolute Galois group of the Gaussians that this action is factoring through, and it should be some like evident.
Yes. I mean, right, these absolute abelian Galois groups, or even these absolute Galois groups, these are very pro-finite or something like that. You know, you just see a little bit at a time as you start adding more and more irrationalities for the symmetries to act on. So if you just have, like some quadratic irrationalities, and that's all you got, you're just seeing a little Z mod 2 quotient of the Galois group. But as you keep on unfolding, you get these, more, these profinite things that are less and less finite. And
it seems like there should be some particular one of those finite quotients that this picture is sort of supposed to focus our attention on.
Yes.
And I can't tell what it is. What is it?
Well, I mean, it's the image of the action of that big profinite thing when it's acting on these 13 torsion points of the lemniscate. So there's some 13th degree, am I saying this right? Is it really going to be 13th degree? Or 12th degree? Sorry, it's going to be something like that. No, actually, you have to count the number of, there's probably 12 primitive torsion points here, I think. Unless I'm confused, it seems to me any one of these 12 points in the middle will be equally as primitive as any of the others. So I have a feeling it's like a 12th degree equation. So this would be, acting on the roots of this 12th degree equation for the primitive 13 torsion points on the Gaussian lemniscate.
Okay.
And everything is going to be like that. I'm explaining it horribly. I'm not explaining it well yet, but this is what it's going to be. When we really understand what's going on, it's really just going to be telling us that you stare at the graph paper and you interpret it in two different intuitive visual ways. One is that you're staring at these quotient rings of the integer ring, of some number ring. You're staring at some finite quotient rings of some number ring. And you're getting the GL1 of that quotient to act on the elements of that quotient ring. And the other thing is there's this very abstract Galois group. It's very hard to visualize, very hard to understand, but it's agreeing. It's really the same thing. And it's the abstract action of that on these torsion points. I'll have to explain it much better than this later, but is that anywhere close to making sense yet? I mean,
Yeah. It makes sense. I was just hoping that
yeah,
when you talk about the Galois side,
yeah,
that, well, you gave one that the absolute Galois group action would factor through some really much more manageable finite group. And so you gave one description of it, which is that it's,
yeah, it's this 12 element cyclic group. So we're saying that there is this 12 element cyclic quotient
right,
of this absolute abelian
right.
Galois group
Yeah,
of the Gaussians.
yeah. Well, you described it as like, but I wanted like a description of it, like it's the Galois group of something. And I want to say that something is like some idea that you get by blending the idea of the Gaussian integers and this ideal in the Gaussian integers. So I don't know how to do it. So, but you were doing it this other way where you say you take the degree 13 equation.
Order 13, yeah, the degree 12 equation for the primitive order 13, the primitive 13 torsion on the Gaussian landscape.
Yeah. So, okay, that's, yeah, so that's still a, that may be all the best you can do. That's sort of a description that's very much phrased in terms of the elliptic curve. Maybe it has to be. I was thinking there might be some description that's more phrased purely in terms of like a number ring and an ideal in that number ring, because that's like another way to think about what you've got here.
Yeah, but that's the other side. That's where you say you have the, you just take the general linear group of that, and it's acting on the that quotient ring.
Yeah, I was wanting a Galois group description that's over on the other side, but okay, maybe that's.
I know that there's a whole bunch of mistakes I keep on making here, a whole bunch of traps I keep on falling into. So,
I mean, so you're saying there's some order 12, 13, 13.
I mean, it's the usual thing of, the field is size 13, but it's only got 12 units in it, 12 non-zero elements in it.
Yeah. Anyway, you're saying that there's some quotient group of the Galois group, absolute Galois group of the Gaussians that has that size. Yeah, anyway, I guess I sort of get it.
And yes, and when we straighten this out, one of the things that's supposed to be clear is that what we're doing for the torsion points on the Gaussian lemniscate is really just a follow-up chapter to the original story that we had about the torsion points on the multiplicative group of the complex numbers. Yes, I mean, right. That's the
cyclotomic stuff. I mean, yeah.
Yes, the cyclotomic stuff. Right. That's right. So there's this, there's this whole story about the torsion points on the cyclotomic stuff and how that's related to the GL1 for the finite fields.
Mm-hmm.
And now we've got a retelling of that same story, but in this fancier context, where we're dealing with the Gaussian lemniscate instead of the multiplicative group of the complex numbers. So the multiplicative group of the complex numbers, that's like GL1 over the complex numbers or something like that.
Mm-hmm.
I mean, there's something, right? There's something going on here where GL1 of the complex numbers is appearing on one side of the stories and GL1 of these finite fields is appearing on the other side of the story. But when you generalize that, I'm not sure if you still have GL1 on both sides, you have something else on both sides. Anyway, we're really going to have to get these stories to make sense. I hate the idea of falling back on pictures and thinking through pictures without really understanding the stories. But that it clearly is what I'm doing at this point. I'm claiming that there really are pictures that make sense. But the point isn't to wallow in the pictures from my point. The point is to use the pictures to guide you to be able to really get the stories to make sense. So I'm still struggling to do that.
Uh-huh.
So
okay, well, good. I hope.
Okay.
I hope
So
you give me another shot of it next week. Oh,
okay.
wait. But no.
Okay.
Because next week I'm going to be busy.
Okay,
So
Okay.
the week after that, yeah.
okay, that sounds reasonable. Okay, so thanks a lot. This was very helpful. I still need to work more at it and clarify everything, but I'll keep going. Okay,
Okay, doke. Sounds great.
okay, thanks, bye.
Yep, see ya.
Okay.